All right, so this week we're going to look at just one section in the book, okay, back in chapter 2, okay, section 2.4, and it's on graphing trig functions. Specifically, out of the 6 that we've studied, the sine, cosine, tangent, secant, cosecant, cotangent, we're only focusing on sine and cosine. Okay. So I showed you guys a graph a little earlier of that. So there's a graph of sine, and it's got this nice kind of wave shape to it. It's called a continuous function because if I marked 2 points on that graph, so let's just take the graph, I could mark 2 points anywhere I want, and if I said to you to trace between those 2 points, you could do it without ever lifting your pencil. If you can do that, it means it's continuous. On that other graph I showed you earlier, kind of looks like this. If I marked 2 points there and said to trace between them, you can't do it without lifting your pencil. Okay? It's kind of like you trace part of a section, then you got to lift, and then go to the next section. Okay? That is not a continuous graph, but the ones we're looking at this week are. Another thing that this graph is called is periodic, meaning it kind of has a pattern to it, and it just repeats itself. Okay, here's the pattern that we're looking at. Okay, what I just traced in black. If you copy and paste that section in black, left and right, that's how you get this graph. It's the same exact thing, just repeated over and over, going in each direction forever. Okay, so there really is no end to these graphs. They go on forever. Okay, so we'll write some of those important things down. What we're going to focus on with the graphing is transformations. Okay, that's the basic graph that I just showed you. But we can do 4 things to it. We can move it left and right. That's one. Vertical. That's up and down. That's the second one. We can stretch or compress left and right. And then we can stretch or compress vertical, up and down. Okay, so there's really four things we can do. Today we're going to look at 1 transformation. Tomorrow we'll do 2, and then Wednesday we'll do 1. Okay, and as we go through the transformations, what I'm going to try to do on at least 3 out of 4 of them is kind of show you a connection to sound. Okay, so these kind of waves are perfect for modeling sound frequencies. Okay, so here's a program which lets me generate different frequency sounds. And out of the 4 transformations I mentioned, I can demonstrate 3 of them and let you hear what they would sound like. So I can do shifting left and right. Okay, that's kind of like that. And we'll hear what that one sounds like today. I can't shift up and down. With sound, there's no connection to that really. But I can stretch up and down. So that's compressing. That's stretching. And then I can also stretch and compress left and right. So that's compressing. And that would be stretching. And all of those have a different effect on what it would sound like. If I, let's see. So this, obviously the microphone is on right now, so if I bring up the program I use for recording, I can show you a picture of my voice. I just need to find the right thing that'll show me a picture. So this is showing you a picture of the different sound frequencies in the room. Okay. I don't know if you noticed, but there was a slider here that said frequency, and frequency is measured in hertz. Right? So as I change it, I can make higher pitch sounds, or I can make lower pitch sounds. And this is a picture showing you every frequency in the room right now. So there's a lot of low frequency noise in the room, and that's probably because of the like the heating system. Like there's a really low hum, whether you can hear it or not. My microphone can pick it up. And I adjust for that. So that yellow line is what the microphone picks up. And that faint yellow line is what it would pick up if I didn't adjust it. So most of that low frequency noise is cut way down. There's also a couple other frequencies that I completely get rid of when I record. Does anyone have a guess of what frequency I completely cut out when I record so you can't hear it at all? Yeah?
Radio frequency?
Well, radio frequencies, those are a little different. That's an electromagnetic wave, so we don't hear radio frequencies unless you have a radio. We would actually see radio frequencies if our eyes could see them, but our eyes can only see visible, so we can't see them, but that's a good guess. Does anybody know what other sound I wouldn't want in the recording? A single pitch noise that I want to cut out completely? The bell. I really don't want the bell in the recording. So if I want, I can make it so that one sound is not picked up by the microphone. Does it really affect my voice? No, because you can see as I'm talking, my voice has thousands of millions of frequencies in it. That's what makes my voice sound like my voice and not your voice. And if I just take that one single frequency out for the bell, it doesn't really affect how my voice sounds at all, because there's millions of other frequencies in my voice. So if you listen to a recording, you won't hear the bell very well. It's because I cut that frequency out. Right? It's all kinds of different stuff we can do with frequencies, and if you get into like audio engineering and mixing music and making songs and stuff like that, there's a lot more you can do with frequency, but just kind of showing you one little thing. Okay, so the two graphs that we're going to study are sine and cosine. And again, those are called periodic functions. What periodic means is that there's a pattern to it and it repeats over and over. But it's predictable how fast it repeats. So if we bring that picture back up and you focus on 2 points. Let's say you focus between here and there, where I just drew those two imaginary lines. That graph cycled one time. A full cycle is up, down, and back up. How fast or how many times it cycles in between those two sections, that's what we call the period. So now if I do something like this, it's cycling a lot more than one time in between this and that. Right? So that would have an effect on what we hear. But the point is, it's predictable. The speed at which it's cycling never changes in that whole graph. Okay, you could measure it, and it's exactly the same. Sometimes we call that a wavelength, measuring the distance between corresponding points. Okay, so it's a periodic function because the y values repeat over a given set of x values. So the y values that a sine or a cosine function can basically take on are anything between -1 and 1. Okay, if you look closely at the graph I have right there, that's the graph of sine. It says sine at the top. The highest it goes is 1. The lowest it goes is -1. So, all the possible y values here consist of starting at 0, going up to 1, back to 0, -1, back to 0. That's a cycle. 0, 1, all the way down to -1, and then back to 0. So what I just traced is one cycle. The question is, how wide is it from here to here? In between those two black lines is one cycle. And For our graphs, we call that length the period. So the period is the x values that you have to move through before you get one full cycle. After one full cycle, things are just going to repeat. So what that means is if you can sketch one cycle of this graph, then you know what it looks like forever. You just have to copy and paste that one section that you sketched over and over. For sine cosine, the length of the cycle, if you don't do anything to it, it's measured in degrees or radians, and it's 2 pi. So 2 pi radians, or 360 degrees. So what that means is if I wanted to just show you one cycle on this screen, what I could do is just draw it from 0 to 2 pi. So what I just did is I changed my screen. I'm not going to show you as much on the x-axis. I'm going to start at 0. I'm going to end at 2 pi. And if I do that, you're going to see exactly one section of the graph now. When we make a sketch, that's how we're going to do it. You're just going to show me one section of it. Any questions on that? Now, it might look like I just stretched that graph out a little compared to this, but I actually didn't change the graph at all. All I did was change where you were looking. So I decided to zoom in to that section right there. But I didn't actually change the graph at all. It just looked bigger because I zoomed in. I already mentioned that idea, but the graph repeats itself over and over. And another name for a period is also called a cycle, one cycle of the graph. Other trades and disciplines, they use the word cycle. We use the word period more. Is anybody in electrical? Cassandra? Do you, there's something that you measure with electricity in cycles per second. Do you know what that is that you measure in cycles per second? Motors. And do you know the abbreviation they normally use for that? They don't normally do cycles per second. It's a two-letter abbreviation. Not sure. Anybody know? It's not voltage. Voltage is something that's important. All the voltage in this room for the outlet should be 120 volts. But they also have to be something else, so when you plug it in, your device won't work right. Anybody know what else you have to keep the electricity at? The what?
Start with J.
The what?
So does it start with J?
J? No. No. Anybody seen this before? Hertz?
Yeah.
Yeah.
Hertz. So, in this room, and every outlet in the US, standard outlets, should run at 60 hertz. If you look at like your charger for your phone, there's a bunch of little writing on it. You'll probably see that number on it somewhere. You'll see 120 volt, and you'll also see 60 hertz. So, without really getting into a lecture on electricity, in this room we have alternating current. Your car is direct current. That's different. So, in your room, in your house, alternating current runs at 60 hertz. That's how many times the electricity cycles per second, 60 times. Not every country uses 60. Some use 50. So if you go to Europe and you plug in something that's only works on 60 into 50, no good. You're gonna fry whatever it is you're plugging in. Something like a light bulb, like a basic light bulb, nothing fancy, might work okay for a little bit. But anything that has like sensitive electronics in it, like transformers, computers, things like that, motors, if they're not designed to run on that frequency, they won't work right. If you have a generator at your house, anyone have a generator? Yeah, sometimes if you have a cheap generator and you measure the hertz, it might come out at like 58, it might come out at like 62, be a little off. And I've measured it because I have a thing you can plug into it and you can measure it. And I can tell when the motor on my boiler is running, okay, that it's a little off. Like I just know what it sounds like because I hear I'm used to hearing the boiler run when it's heating the house. And I can tell when it runs on the generator, the motor sounds a little different. And that's because the electricity coming out of my generator is just a little bit off. Short term, probably not a big deal because it's only like 61 hertz. It's close. But if long term, what that'll do is the motor will run a little hot. And over time, if I were to run my boiler forever on a generator, the one that I have, it would probably wear the motor out faster. Okay. So cycles per second or hertz, that's what any trade that uses electricity, that's what they would measure it in. Okay. So we'll stick with the name period, but the name cycle is another name. All right, so these kind of graphs are a little bit more complicated than just like a line or a circle. Okay, lines and circles, you can get away with drawing a line just 2 points. Circle, you can get away with just 3. Any 3 points determine a circle. But with these kind of graphs, we really need 5 points. Okay, and I call these the 5 important points, or the 5 key points. We've got the starting point, the stopping point, the highest, the lowest, and then what's right in the middle. If you can get those 5, it'll give you a pretty good sketch. You can always get more than 5. We're not gonna. But we're gonna get 5 points. And if you notice, those 5 points are all equally spaced. One here, 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 there, and then at the end. Now, earlier I told you how long a cycle is. Does anyone remember what I said the period for sine and cosine was? I said it was this many radians, and then under I put this many degrees. Yeah?
You put 2 pi radians or 360 degrees.
2 pi radians or 360 degrees. So if you have 360 degrees to get from here to here, and you're doing it in 1, 2, 3, 4 sections, right? Those lines I drew in basically separated into 4 sections. How far apart is each line if they're all equally spaced? Jordan? If you have 360, pretend you're driving 360 miles, you're going to get there in 4 days, and you're going to drive the same amount every day. How far would you have to go each day? $90, yeah. These are all 90 degrees apart. Each one is 90 degrees apart. We're going to write it in radians, but in degrees, that's 0, 90, 180 is the half point, 270, 360. Again, we're going to do it in radians, not degrees. So, anytime you want to graph a transformation or sine or cosine, you have to know where it starts. If you don't know where the graph starts, you're not going to be able to figure out where it's going to move to. It's kind of like if you asked me how to get somewhere and I said, oh, it's just 2 miles that way, 2 miles east. Well, if you're talking to someone else and they don't know where you started from, 2 miles east doesn't make sense. 2 miles east from where? Where'd you start from? Well, this is where we're starting from, this picture. Okay, so we're going to write down the coordinates of those 5 green dots you see in that picture. and we're going to put them in a table. Okay, so what you're looking at right there is the graph of sine. I haven't shown you the graph of cosine yet, but it's almost the same. Okay, I'm going to put cosine in blue right on top of the one in red. The only difference between sine and cosine is you can think one of them is pushed to the left or to the right, depending on which one you're looking at, of the other. But they're very, very similar. But they're not identical. Okay, they're a little bit different. So, we're going to start with the values for sine. And these are the numbers from 0 to 360, spaced every 90 degrees. So you've got 0, pi over 2, pi, 3 pi over 2, 2 pi. 0 to 360 going in 90-degree increments, but we've written it in radians. Okay, so now let's look at our graph and see if we can get the coordinates. So Tanner, for my first coordinate, when x is 0, what's my y value right there?
0.
0. So the first coordinate is 0, 0. We'll do cosine after in a second. Brady, my next one is pi over 2. When I'm at pi over 2, what's my y value? 1. So we're at 1. Pi is the halfway point, right there. Caitlin, when I'm at pi, what's my y value there?
0.
Yep, we're back to 0. 3 pi over 2 is the next one. And now we've hit the lowest value, negative 1. And then 2 pi is really a repeat of 0. Okay? Because here, you could look at that point as the end of that cycle, or it's the same point that starts the next cycle. So it has to end back where it started, at 0. Okay, so those are the 5 critical, the 5 key, the 5 important, however you want to think of it, points for sine. Everything we do is based off that table for sine problems. Okay. For cosine, we have a little bit different table. Same x values, because we want to pick x values that are nicely spaced. So the x column controls the spacing. So we've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. But let's look at our graph in blue. Okay, I'll get rid of the one in red so it doesn't look confusing. And remember, we're only focusing from 0 to 2 pi. So ignore everything else you see. Just focus on that section right there. That's where it ends. That's where it starts. So when x is 0 this time, we're at 1. So we start at 1, 0, negative 1, 0, and we end where we started, back at 1. So if I give you a problem involving cosine, start with the table on the right. Sine, table on the left. Any question on those two tables? All right, so when we graph a transformation, okay, that means shifting it left, right, shifting it up, down. Whatever I ask you to do, there's 2 things I'm going to be looking for in that answer. 1, show me the new table. Okay, this is the original table. When you move it, say, up 2 units, tell me what the new coordinates would be if you take all of those and shifted them up 2. So I'm going to look for the new table, and then I'm going to say, draw a picture. Show me what it would look like if you did that on a graph. Okay. So this is the first part of what I just said. Show me the table. Tell me what the 5 coordinates are for your new graph. Now, the way we're going to do transformations, we're only going to do one transformation at a time per problem. So what that means is if I have you shift the graph up in the problem, that's all you're going to do. You're going to shift it up. You're not going to shift it up and shift it left. Okay, that's two transformations. In pre-cal, we get into multiple transformations because we have more time, but we're only going to do one transformation per problem. So when you do one transformation, your transformation is either going to affect the x-axis or the y-axis. If you shift vertically, that affects the y values. It doesn't do anything to the x's. If you shift horizontally, that's the opposite. That would affect the x's. It would not affect the y's. So the point is you're only going to be affecting one variable per transformation. The reason we don't get into multiple transformations too much is because once you get into multiple, then order becomes important. Okay. It could make a difference if you stretch something by a factor of 2 and then shift it up 7, or shift it up 7 and then stretch by a factor of 2. It's kind of like PEMDAS. There's an order you have to follow. And we really, that would be kind of the next lesson if we had another week to look at stuff. Okay, so any questions about what I've tried to explain so far? So everything we just explained, that was all just kind of background stuff about sine and cosine. For the rest of the week, now I'm going to talk specifically about each transformation. And there's 4. So the first one we're going to start with is a phase shift. So when I ask you about a transformation, the first thing you have to know is if I give you something like that, you have to be able to identify out of the 4 transformations, which one is that. So we have to look at the equation, know the type, and then once you know the type, you have to know, well, what does that mean? Like if you just tell someone, oh, I have a phase shift, that's not really intuitive of what it does. Okay? I think vertical shift is kind of a little more intuitive. Vertical, somebody might say, oh, it does something up and down. Well, phase shift means it moves left and right. Okay, and how do you know looking at an equation? A phase shift is when you add or subtract. Adding is going to control moving one way, subtracting is the other, inside the parentheses. So you've got your trig function, sine or cosine, and then inside the parentheses, or inside, we call that the argument, you add or subtract a number. Okay? Whatever you add or subtract, that's going to control how much it shifts. Okay, let's look at not something as complicated as sine, but something a little simpler. You probably did in Algebra 1. Let's just look at a square root. That's what the graph of the square root function looks like. It's kind of this curve. Now, I'm going to add something inside the argument. I'm going to do square root of x plus 2. It's kind of like the same idea as sine. I'm putting a plus 2 inside the argument. Okay. I'm not putting it outside. Okay, that's outside. It's inside. So plus 2 is either going to move it left or right. Does anyone have a guess which way it's going to move? Yeah? Right. Okay, so plus, you might think on the number line. Positive numbers go to the right. Negative numbers go to the left. Let's see what happens. So when I did a plus 2, it moved it left. It doesn't look like it moved 2 units because I didn't have my window on the calculator set, but if you look now, it'll definitely look like it's moved 2 units. Okay, so it shifted it 2 units. And that idea of adding, shifting it left, is also true here. In fact, that's true in every single function you could ever study. Square roots, squaring, cube roots, logarithms, no matter what you study, if you add a number inside the function, it will always shift your function left. If you subtract a number, it will shift it right. So again, we're just studying trig functions, but this rule that I'm writing right here applies to any function you could ever study. If you ever do a phase shift and you subtract a number, it's going to shift your graph to the right. If you're doing a phase shift and you're adding a number inside parentheses, it's going to shift it left. Okay. Not necessarily intuitive, right? A lot of people, I bet, thought positive goes to the right because that's how you think on a number line. Well, when you do a phase shift, it's the opposite of what you would think. And that's something that'll usually trip people up on the test. They'll forget to do the opposite. And what makes it a little more confusing is out of the 4 transformations, 2 of them do the opposite of what you would expect. 2 of them do exactly what you would expect. Phase shift is one that does the opposite. So somehow you just have to remember, phase shift does the opposite. Okay, so I'm going to go back to the sound program and just show you again some shifts. And I'll play it, and I'll let you hear what a phase shift sounds like. Okay, so first I'm just going to put the frequency right at around 1,000 hertz. Okay, that's not going to change. Okay, that's the pitch of the sound. So everything that I play, it's Bluetooth, it has to connect. It's going to sound like that. Okay, that's 1,000 hertz tone. Now I'm going to change the phase, okay, and see what we hear. We'll turn it up a little bit. Maybe not that loud. And as I change the phase, you're going to see how much I'm changing it by. It's a shift in degrees. Now, technically, you can shift by any amount you want, including 29.16 or 70.56. You don't shift by those amounts. Okay? Generally, we're not going to shift by decimal amounts, even though you can. We're going to shift by nice amounts, usually 45 degrees, 180 degrees might be a common one, 90, anything like that. Okay? We kind of stick to ones that are multiples of 45, just because the arithmetic works out a little nicer without decimals. But technically, you can shift by anything you want. All right, so as I play that, I want to put it back at the beginning. Did anyone have a guess what it's going to sound like as I shift the phase? Cut?
Higher pitch.
Higher pitch? Okay, so the pitch could change. What else can change about a sound besides its pitch? Do you mind? Well, the sound itself, if you change the pitch, I guess they could change what vibrates in the room. Like, we can talk about resonance. Different objects in this room resonate at different frequencies. And if I play the frequency loud enough, I can make objects vibrate, like glass. You can make glass vibrate. That's usually not a good thing. And other things too. But that's not quite what I'm looking for, because that kind of ties in with the frequency or the pitch. What else can you change about a sound? What about the radio in the car? What do you do with that? can change the volume of the sound. Those are really the only two things we can change in this program. I can change the volume of the sound, I can change the pitch of the sound. So one of those two things is going to be affected when I change the phase. Let's see what happens. So what happened as I changed the phase? Mikey?
Got louder.
It got louder to you? I'm just asking, it got louder?
Yeah.
Okay.
It seems like it got louder.
It got louder. Okay. Anyone else think it got softer? No? Jordan, can you come up here for a second? Just, I'm going to have you stand right where I was standing, and I'm going to play the sound from my desk, and I want you to tell me what you hear. Standing right there. All right. What happened for you?
Okay, so it went really loud, then it got a little bit quiet first, and then it went louder again, so it kind of was like a wave.
So it kind of changed. So it didn't just get louder the whole time.
Well, no.
Okay, like so, yeah. So yeah, thank you. Yes. So depending on where you stand or sit, you might hear different things because there's a lot of complicated things happening. So when I change the phase, it's like the left and the right speaker. Sometimes they're fighting each other, and if you stand at the right spot, you can almost get it to a point where you don't hear anything at all in the room. So another way to do this would be is instead of me changing the phase, you walk back and forth. Okay, if you were to walk back and forth, you would hear the same effect that I can do with you just sitting in your seat by dragging the phase. For me, that one is pretty soft. Okay, when I put it here, it's much louder for me. Back at the beginning, it's a little softer. So it kind of changes depending on where the phase is. All right. And same thing, if I drag the right, so for me, it got kind of loud towards the end. It got kind of soft in the beginning, but it all has to do with the shape of the room, the way the sound is echoing, and the left and the right speaker are kind of either reinforcing each other, giving you a louder sound, or fighting each other. But even though you heard a change in volume, there was no change in volume. You heard that, but I actually didn't touch the volume slider the whole time. All right? So that idea gets really important when you're creating like an auditorium or a music hall. You want to set up the room so it has good acoustics. If it got really soft for you at one point, that was kind of like a dead spot in this room. That's not good. So if there was a band playing and something sounded really soft in one spot of a room, people don't want to be in that part of the auditorium or the music hall because it's a dead spot. It just doesn't sound good if you're sitting in that spot. So they can do all kinds of things to make a room acoustically sound better. This room is really pretty bad for acoustics because there's a lot of hard surfaces. There's cement walls, there's the glass, smart TV, all kinds of hard surfaces. So what happens is the sound is bouncing everywhere. Okay, so that's why on the mic, one thing I have to do is to cut out echo. Because you don't hear it a lot in here because it's pretty small, but when this room is empty and you talk, you really hear an echo. Okay, all of you kind of mess up the sound bouncing around because you have shirts on and clothing kind of absorbs sound. It doesn't bounce off it like a desk. Okay? Desks are hard surfaces, walls are hard surfaces. So there's lots of weird things happening in here with sound, but that's what a phase shift sounds like in this room. If you could do it outside where you have no walls around you, just put two speakers kind of aimed at each other like 100 feet apart, and you walk back and forth changing the phase. There might be a dead spot where you don't even hear the sound at all because the sound can't echo back. So you could find a spot where it cancels the sound out completely. And some people have headphones that do that kind of thing, like noise canceling headphones. Does anyone ever use those? Yeah, kind of cuts out the background sound, or if you're on an airplane, you can't hear like the jet engine kind of sound. It just cuts out those frequencies. And cars do that too. Certain high-end cars have what they call phase canceling, and they make the engine sound quieter by canceling out the engine noise with other frequencies. Just, you can read about it. But like expensive cars, not low-end cars.
A lot of the gaming headsets now have noise canceling on it.
Yeah, cancels out the noise. So, yeah. So that's the idea of a phase shift. You can cancel out sound. Now, that's an easy sound to cancel because it's the same frequency tone, mathematically very, very simple. If you want to cancel out my voice, you can try. Some people are more successful than others at this moment. But the problem with my voice is it has thousands, millions of frequencies. So how do you filter millions of frequencies? That's a little harder. Oh. See, it's hard. So the last thing we're going to look at before I show you 3 examples, and that'll be it, is how do you find the 5 key points? You've got the originals. How do you shift? Well, first of all, we're shifting left and right. When you shift left and right for a phase shift, that has no effect on up and down. You're not focused on one peak of a wave. It's just moving left and right. The Y value is staying the same. So you're going to look back at the original tables I gave you, copy down the Y values, and that's it. So there's no calculation at all for the Y values. Well, if the Y's are staying the same, the X's are all going to change. Okay, first thing we want to look at is what did you add or subtract? So in this problem that we're going to do in a minute, example 1, I am subtracting pi over 2. So you identify what you're doing, but then do the opposite. And I tried to show you earlier why you do the opposite. Okay, we looked at it. Plus shifts left, minus shifts right. It's the opposite. So if I see a minus pi over 2, I want minus to shift the graph to the right. How do you move a graph to the right? You make all the x's bigger. If you make the x's bigger, they move right. So in that problem, you're going to do plus pi over 2 to each of the original x's. And that's basically it. That's the whole problem. We're going to leave our answers as fractions. Okay? You don't have to worry about, well, what's 0 plus pi over 2 as a decimal? It doesn't matter. We're just going to leave our answers as fractions. Okay? No decimals. Okay, so make sure you do the opposite for a phase shift. Okay, any questions on the 2 steps? Okay, so let's look at this graph. Okay, what I've done here, I'm not going to do it on every problem, but I put the original table, so you already have that in your notes. I just copied it so I didn't have to flip back to the previous slides. Okay, so we're going to make a table for our new graph. Sam, what's going to stay the same because this is a phase shift? What doesn't change?
The first point.
No, the first point is going to change. Remember, it's going to move, right? And if one point moves, they all move together. So for a phase shift, what stays the same?
The wave. The Y's.
The Y's, yes. The Y's stay the same. Okay? So copy those down from the original table. 0, 1, 0, negative 1, 0. If you get that part right, you get 5 points because you get 1 point for each number in the table. Okay, so that's how that part works. If you get the x's right, 5 more points. So on a test, the table itself is worth 10 points for the question. All right, so let's take our x's. I'm going to put the final answers in that box in the table. I'm just putting the numbers next to the box that I need to do the calculation. So pi, 3 pi over 2, 2 pi. And Ethan, what am I going to do to all those x values to get my new x values?
Minus pi over 2.
All right, I like the idea of using pi over 2. We are definitely going to do something with pi over 2. But what does step 2 say to do? So you're right with the pi over 2, but we're not going to subtract it.
Add it.
We're going to add it, yes. So look at what you've done and then do the opposite. Okay? You always have to do the opposite. So we're going to do plus pi over 2. And I'm just going to write that in for all of them. Okay, now we'll do that out. Okay, the first one, that one's pretty straightforward. 0 plus pi over 2 is pi over 2. Now, to add fractions, you need common denominators. The next one, we already have a common denominator. It's 2. So Tanner, if I add pi over 2 plus pi over 2, what would I get?
2 pi over 2?
Yep, exactly. So you get 2 pi over 2. Which I'm going to leave as 2 pi over 2 because I'm going to show you something with a pattern, but we do want to reduce it to pi for the final answer. Okay, the next one. It's pi plus pi over 2. Okay, Lauren, pi isn't a fraction, so how could I make it a fraction?
Just put it over 1.
You can put it over 1. Unfortunately, we don't have common denominators. We have pi over 1 plus pi over 2. So off to the side, because I don't have enough room to really do this nicely in the table, I'm going to add those in. Ryan, what would my common denominator be? 2. Okay, the one on the right already has it. The one on the left, I need to double the bottom, double the top. So now I have 2 pi over 2 plus 1 pi over 2. Alan, what's 2 pi over 2 plus 1 pi over 2?
3 pi over 2?
Yep, 3 pi over 2. So there's my next coordinate, 3 pi over 2 comma 0. The next one, I already have a common denominator. So Jamaica, what's 3 pi over 2 plus 1 pi over 2?
4 pi over 2.
Yep, and I'm going to write it the way he said it, but then I'm also going to reduce it. To 2 pi. And the last one, I would need a common denominator. Double the bottom, double the top. 4 pi over 2 plus 1 pi over 2 is 5 pi over 2. Hey, bless you.
Thank you.
Now, look at the pattern before we reduce the answers. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If we were going to start graphing the next section, what do you think the first x value would be? Yep, it would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. That's the pattern here. If you do this properly, you will always see a pattern. Once you reduce it, do you really see a pattern? No. Okay. But if you don't, you can at least see the pattern, but then reduce it for the final answer. Yeah.
You want them reduced, right?
Yes. Yep. Okay, so now we're going to make our graph. Okay, when you make a graph, it's important that you space things consistently. If you were numbering this, you can't go like this. 1, 2, 5, 6, 7. It's not spaced evenly. Okay? If you're going to go by ones, go by ones. If you want to go by threes, then go by threes, but don't switch halfway through. Well, these original values were all equally spaced. If you take a bunch of values that were equally spaced and you add the same number to all of them, are they still equally spaced? Yeah, these are still equally spaced. If you wanted to know in degrees, that's 90, 180, 270, 360, 450. It's just plus 90 each time. So I'm going to use those to label my x-axis. Pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. That's the easiest way to label your axes. I would not label them 1, 2, 3, 4, 5, 6, 7. Because none of your x values are nice numbers. These are all decimals. Like 3.14, 2 pi is 6.28. That's a mess to graph. So that's why we're going to label our x-axis like this. Okay, and Carissa, what's my highest y value in that table?
5 pi over 2.
Y value.
Oh, y.
That is the highest x value.
Would be 0. Or, no, would be 1.
1. And what's the lowest?
Negative 1.
Negative 1. So we're going to go from 1 to negative 1. Now, sometimes, because we're about to make a sketch, people put these labels a little lower, just so you don't end up drawing over them. If you want to move them down, that's fine. If you draw over them, that's fine too. Okay, so now we just graph our points. So we've got pi over 2, 0. Pi, we're at 1. 3 pi over 2, okay, back to 0. 2 pi, we are at negative 1. 5 pi over 2, back to 0. Sometimes it gets a little squished, but I can see the points. They look like a nice wave. And when you connect it, just try to make it look as smooth as you can. And it shouldn't look like that. Okay, so there's our new graph. Okay, if I trace over it, the original would have been right there in black. You don't have to sketch the original. I'm just showing you where it would have been. And the red one has been shifted to the right, pi over 2. And that's exactly what should happen. When you subtract, it should shift. Okay. Any questions on that one? Okay, so that's a shift by pi over 2 using sine. Let's try a shift by pi, this time using cosine. Okay, I'm not going to copy down the original table. You already have it in your notes. So we'll just write the final table. Okay, so we already know it's a phase shift. It's the only transformation I've taught you, so it can't be anything else yet. Emma, for a phase shift, what are the two directions we could move for a phase shift? Left and right. And left and right is along which axis? X. So it's the x's that are going to get changed. The y's stay the same. So now I need to just fill in my y's from my original table. Justin, can you remind me what my y's are from my cosine table?
1, 0, 1, 0, 1.
Perfect. 5 points for that column right there. Okay, the x column is 5 points. The sketch at the end is usually, I think it works out to be like 2, the way the numbers work out. Okay, but the table is most of it. Now we're going to take the original x's, Ben, can you tell me what are my original x's for cosine?
0, pi over 2, pi, 3 pi over 2, and 2 pi.
Yep. So there's my originals. I'm going to put all my final answers in that box. And Austin, what am I going to do to all the values that Ben just gave us?
Subtract pi.
Right, we're going to do the opposite of adding pi, minus pi. Okay, 3 of these are pretty quick. 0 minus pi, pi minus pi, 2 pi take away 1 pi. Now the rest of them, I need a common denominator. Or there's another way to think about it. You've got a coordinate and another coordinate, and the one between it is equally spaced. It's halfway between the other two. So if you can think about it that way, you can do it. I'm not going to get into that. I'm just going to show you how to do it with subtraction. Kyle, what's my common denominator here?
Pi.
So pi is in the
sorry.
numerator. We need common denominator.
2.
2. So we're going to double the bottom, double the top. And Sean, what's 1 pi over 2? Take away 2 pi over 2. Over 2, yeah. We keep the denominator the same. It's negative pi over 2. Now, if you've got 4 out of 5 points in a table, you should be able to look for a pattern and just figure out the other point based on the pattern. If you wanted, you could write the top one like this. Negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2. The last one is 2 pi over 2. So what do you think the middle, the one that I'm missing right here is without doing the subtraction? Yeah.
Positive pi over 2.
Positive 1 pi over 2. And then 2 pi over 2, 3 pi over 2, 4 pi over 2, and so on, if you were going to keep going. Okay? So what you're looking at right there, that's 10 points for this question. Last part is to just sketch it. All right, so let me make it like this. Okay, so we have negative pi. So this kind of requires a little planning on how many marks you go over. I have 2 negatives, so I'm going to go over 2 to put negative pi. Negative pi over 2. 0 I don't need to label, that's the axis. I know it's 0. Pi over 2 and pi. Okay, you have to put those other labels. If you don't label your axes on a problem, I'm going to assume you're going by ones, because that's normally what we do. So if you want to go by something other than ones, just label it. Okay, I'm just going to move them down a little bit. Every graph today has a high value of 1 and a low value of negative 1. Okay, so we get negative pi. We're at 1, 0, negative 1, 0, back to 1. Now it looks kind of like a V shape, but remember, those are the kind of graphs we're looking at this week. And you're sketching that section right there. So just try to make it look a little curved. Any questions on that one? All right, so last one. So this is a shift going back to sine, but it's a shift by pi over 4. Okay, so I'm going to go through the table for you quickly because I think you could do the arithmetic and figure it out. But I want to show you what happens when you graph this one. Y's stay the same. x's. I'm going to take 0, pi over 2, pi. Oops. That up a little bit. Pi. 3 pi over 2. 2 pi. And I'm going to add pi over 4 to all of them. So you might think this is going to require you're going to get common denominators for everything, but I just do the first two, and however far apart they are, that's how far apart they all are. It's the same all the way down. So that's pi over 4, and the next one is pi over 2 plus pi over 4. Double the top, double the bottom, I get a common denominator. 3 pi over 4. There's a gap of 2 between the number and the numerator. So we have a 1, 3, next one's going to be a 5, 7, and a 9. If you don't see that pattern, no big deal. Just find the common denominator every time, do it out, and that's what you'll get. So what's different here, though, is look at the x column. Is there a 0 in the x column? No. There was here. And even though we didn't put it, the point before it would have been 0. Okay? It would have been 0 pi over 2. In this graph, we just completely skipped over 0. Because even if you went to the one before this, it wouldn't be 0. The one before it would be negative pi over 4. 0 is just completely skipped. So let's set up our graph and see what happens. So I'm going to put pi over 4 as the first one. Now, to make this a little simpler, I'm going to do it in degrees below so you can see what's happening. Pi over 4 is 45 degrees. So what you've just done is you made this gap worth 45 degrees. That's fine. That means every gap has to be 45 degrees. Well, this is 45. The next number is 135. How far away is 135 from 45? Yeah, it's 90 away. So you cannot put 3 pi over 4 here. Don't do this. If you do that, pi over 4 and 3 pi over 4 is 90 degrees apart, but you made each gap worth 45. So 3 pi over 4 has to go here. That usually only happens when you're dealing with the pi over 4s. If you're not sure, change it to degrees and look at the numbers and make sure you're spacing them equally. So 45, 45, 45. There's my gap of 90 to the previous point. Okay? This is kind of a weird thing that happens with pi over 4. Okay? That's how you label your axis. Okay? And then your y values. 0, 1, 0, negative 1, 0. And I don't have enough room for 9 pi over 4, but I'll just try to squeeze it in. Should be over a little bit more, but I can't fit it. You'll know if you do a point wrong, because if you draw your points and they look like this, like one part of your graph looks really squished and then the other part looks really stretched, it's not nicely spaced, then you know something's wrong. Okay. Here, they all look nicely spaced, so we're good. Okay, so that's a phase shift. Okay, so homework tonight will be a worksheet. Okay, I'll put the worksheet up in the video in case you need it. And the plan is for a test on Friday.